determine the stability of a system using the Routh Hurwitz Criterion. So let's see the problem. So our problem is that we are given the open loop transfer function of a unity feedback system, and it is GSHS equals to K e raised to the power minus S and divided by S square plus 2S plus 1. And we have to discuss the stability of the closed loop system in terms of the parameter K, that what will be the value of this K and at what value the system will be stable or unstable. So let's solve this problem. We are given this open loop transfer function GSHS. Now, if we see this exponential series, then this exponential series is given by 1 minus S plus S square, and similarly the higher terms for it. So if we neglect the higher terms, then only this 1 minus S will be left. That is e raised to the power minus S is 1 minus S. So replace this e raised to the power minus S, this exponential term, with 1 minus S. So this open loop transfer function, it will now become K 1 minus S upon S square plus 2S plus 1. Okay. So this is our open loop transfer function. Now to apply the Routh Hurwitz criteria, we have to obtain the characteristic equation of this system. Okay, and characteristic equation is given by 1 plus GSHS equals to 0. So let's determine the characteristic equation. Substituting the value of GSHS here, we will have K 1 minus S upon solve this, we will have S square plus 2S plus 1 plus K into 1 minus S equals to 0. Multiply this, we will have S cube plus 2S square plus S is K minus KS equals to 0. So having the same coefficient terms as 1, we are having S cube plus 2S square plus S and minus KS. So it will be S 1 minus K and plus K equals to 0. So this is our characteristic equation for this system. Now obtain the Routh array using this characteristic equation. So Routh array is given by Routh array is, we are having the highest power of S in this characteristic equation as S to the power cube. Okay, so S cube and its coefficient is 1. So putting the coefficient of all the odd terms, we are having S cube s square is 1 and s to the power 0. So coefficient of s cube is 1 and coefficient of s to the power 1 is 1 minus k. Now coefficient of s square, it is 2 and coefficient of s to the power 0 is k. So putting here k. Okay. Now finding s to the power 1, what it will be? It will be 2 multiplied with this 1 minus k minus this 1 multiplied with k, that is minus k, divided by 2. And this coefficient will be 0 because we are not having further terms. Now here next we will have this multiplied with this minus this multiplied with this divided by this term. So we will have 2 1 minus k upon 2 multiplied with k minus 0 divided by 2 1 minus k upon 2. So this and this term, they will be cancelled. We are left with only k. So here k and this is 0. Okay. Now for this system to be stable, the system will be stable when in the first column all the coefficients are greater than 0 and all the coefficients are positive. Okay. So all the coefficients should be greater than 0. That is positive. So here we are having this as a variable. We are having k as a variable here and also here. So we will obtain 2 1 minus k upon 2 greater than 0, and second we have k equals to 0. So we have obtained these two equations or these two values of k. We have obtained the range here. Solve this. We are having 2 minus k minus 2 minus 2k minus k upon 2. So we are having 2 minus 3k upon 2 greater than 0. It will be 2 minus 3k greater than 0, 2 greater than 3k, or we can say 2 is 2 by 3 greater than k. K is less than 2 by 3. Okay. And this we have obtained that k is greater than 0. So we have obtained two ranges of this k. That is a range we have obtained that k should be greater than 0 and it should be less than 2 by 3 for this system to be stable. That means this system is stable for the range of values of k greater than 0 and less than 2 by 3. So we have solved this problem. I hope this problem is clear to you. Thank you.